Welcome to part 3 of the Leuze Technical Safety Series. Today we're going to be talking about safe distance calculation and how to come up with those safe distance measurements. So, as we've talked about before, when we want to figure out, what type of a hazard we're looking at, and if we have hazards associated with machines, and if our guarding is sufficient, the first thing we want to look at is around, under, through, over, the auto anagram that we said before. So if you can reach around the guarding, under the guarding, through the guarding, or over the guarding, then we know we have a hazard that needs to be guarded. So we've also spoke about this before, which is the hierarchy of hazard control. We can eliminate it by design. We can control access. We can provide other safety measures like barriers, signals, paint lines, caution tape, that kind of stuff. Administrative controls, training, personal protective equipment. Today we're going to be talking about controlling the access to the exposures by safeguarding, and then we'll figure out where we need to mount these things, how we can come up with a stop time measurement, and calculate our safe distance. So the safety distance is the calculated distance between a hazard and its associated safeguard. And as you can see here, CSA Z432-03 from our neighbors to the north. In their standard, it states all safeguarding devices shall be securely installed and located at a distance such that the hazard cannot be accessed. And that is the bottom line basis of what our safe distance calculation is. It's how far away do we need to mount our stop device so that we can actuate that device and have the machine stop before we can reach the hazard. So before we talk about our optical type solutions, we'll first talk about hard guarding. So when we look at hard guarding, it's a little different than we do with our safe distance calculation on our active optoelectronic protected devices. Here we need to look at basically just distance and how far we can reach, how large are the openings, how tall is the barrier, things of that nature. So if we see here, we have our CSA, our ANSI, and our OSHA clearances that we go by. So in a situation like this, per CSA, we need a guard that is a minimum of 72 inches or 6 foot around. For ANSI RIA, minimum of 48 inches. And what that gives us is our clearance. So CSA says 20 inches. So if we have a guard at 72 inches tall, we can be 20 inches away from the hazard. ANSI RIA is 18. This is all, of course, assuming that it is mounted 6 inches off the floor per CSA, 12 inches off the floor for ANSI and RIA, and for active optoelectronic devices such as light curtains, that is 12 inches is what the standard we go by. Here's something that a lot of people have probably seen. This is a gotcha stick. Most people have these. A lot of companies give these away. And what it does is it shows you incrementally along this ruler type looking thing the size of the opening and the distance you can be from the hazard. So at the beginning we have a 1/4 inch opening. We move all the way to 2 1/8. Anything above that is assuming it's a 6 inch maximum opening. Anything between 2 1/8 and 6 is the same distance. So basically, if you can take this stick and put it through any opening in the guarding and reach the hazard, then we have an issue. So this is something that some of the OSHA guys carry, and they'll actually use this to determine, with a quick and dirty, how close we are to the hazard. If they can reach it, that's something they can hit you on. So when we look at our light curtains and other optical devices, we have to look at the different ways we can calculate these safety formulas. So here we show by EN 999 safety distance or safe light curtains must be mounted at a sufficient distance from the pinch point or point of operation hazard to ensure that the machine stops before a person's hands, arm, or body reaches that hazard. So this distance, referred to as the safety distance, must be calculated prior to determining the safety light curtain, protective height, and mounting of light curtains on the machine. So this is something that we need to do before we add the safety devices onto the machine. And we also have here as a note that a lot of people don't think about is that regardless of the calculated safety distance, a safety light curtain should never be mounted closer than 6 inches from the point of operation. So even if our safety distance comes out to a distance of 2 inches, it's still not safe to put it within 2 inches. We still would like to see it at 6 inches. So there's 2 formulas we usually use in the United States. The first is the OSHA formula. The second is the ANSI formula. And then our neighbors to the north use the CSA formula. They're all similar, but there are differences, and we'll show you later that we come out with different distances depending on which formula you're going by. So the OSHA version is very simple. Our D sub S, which is our safety distance, equals 63 times the T sub S, which is our stopping time. So 63, which is our speed of a human hand, 63 inches per second, times the time it takes the machine to stop, gives us our safety distance. So, as we said before, the standard we need to think about, or always keep in the back of our head, is that 63 inches per second. That is the value of the hand speed constant when the body is stationary. That's also something we need to keep in mind, as we see here in the little star area. Sorry, I wrote it so small. That for certain applications, we need to use a value greater than 63 inches per second. And this is going to be determined by the risk assessment we do before we get to this step in the process of coming up with a safe distance calculation. So there may be processes where a person is not standing stationary, and that is a situation where we need to look at using a value higher than 63 inches per second, because the 63 inches per second is calculated off of a person standing still. So if there's a person in movement or in motion, then we need to look at raising that number. So for the EN99 version of the safe distance calculation, we have S, which is our minimum safe distance, which is our constant hand speed times the response time of the AOPD, the safety interface, and the response time of the machine, plus our depth of penetration, or resolution of the AOPD. So what is our depth of penetration? Well, the depth of penetration is the maximum travel towards the hazard within the present sending safeguarding device's field that may occur before a stop is guaranteed. So basically what it means is you can reach through a light curtain a certain amount of distance before you will actually trip it. So if it's a 14 millimeter resolution, which is finger safe, there is a certain amount of distance that your finger will pass through that light curtain until it actually trips. And this is the worst case scenario that we're looking at, that you are between the beams equidistantly, and you can maybe get a quarter of an inch into there before you actually trip it. So again, with most safety calculations, we need to look at the worst case scenario. So depth of penetration factors are going to change depending on the resolution of the device or the minimum object sensitivity. And when we talk about that, we mean the resolution of the light curtain, 14 millimeter, 30 millimeter, all the way up to 90 millimeter light curtain, or even a multiple light beam device that has hundreds of millimeters of resolution. So in situations like that, the higher the resolution, so if we are at 100 millimeters between beams, it's going to have a higher depth of penetration factor than a light curtain with a 14 millimeter resolution. So when we look at the ANSI RIA version, we now take all of these into account. So we have our safety distance, which is our speed constant of 63 inches per second times our stopping time of the machine plus the stopping time of the control system plus the response time of the whatever the AOPD is, the light curtain or rotoscan, plus our depth of penetration factor, then we finally get our safety distance. So when we look at our resolution of AOPDs, the way we measure that is the pitch of each of the optic plus the lens diameter. And that gives us the distance from beam to beam, and that's where we come up with our resolution measurements. So normally when we look at light curtain resolution, finger safe is 14 millimeter, hand safe is 30 millimeter, 90 millimeter, 50 millimeter, we're more looking at body safe. So another thing we need to keep in mind is the mounting of that light curtain is going to affect the effective resolution. So if we have a light curtain, if we look here on the right, if we have a light curtain that is mounted only 0.9 meters or 36 inches, then our depth of penetration is no longer relevant because we're not reaching through the light curtain. We can reach over the light curtain. So in a situation like that, our depth of penetration automatically moves to 48 inches, which is quite a bit away. So we need to keep that in mind when we look at the height of our light curtain as well as where we mount it. So if we have the same light curtain, a little bit longer, mounted correctly, now depth of penetration comes into account, and our depth of penetration goes from 48 inches to 0.275 inches. Our depth of penetration factor is not just based solely on resolution. So if it's 14 millimeter, we have to multiply that by, if we go back here, by 6.875 millimeters or by 2.275 inches, depending on if you're in Canada or United States. And that gives us our depth of penetration in millimeters or inches. So at the smallest, which is a 14 millimeter resolution, finger safe, our depth of penetration is 0.95 inches or 24 millimeters. And that moves on up, obviously, proportionally, where we get larger resolutions. So here's quick and dirty of the three safe distance calculations that we just saw. And now we'll take the same light curtain with the same stopping time, apply it to these three formulas, and we'll see how different we come out with. So we'll take a 30 millimeter light curtain with a response time of 15 milliseconds, a machine stopping time of 180 milliseconds, and a brake response time of 40 milliseconds, which is something we didn't really talk about before, but it's something you need to keep in mind if you're looking at presses especially. You need to take into account the brake wear as well. And we'll take a 3-inch depth of penetration factor. So these are the three formulas we just spoke of. Safety distance 17.8 for ANSI, 14.8 inches for OSHA, and 18.5 inches for EN 999. So basically we've gotten a very large spread of safety distances based upon the different formula we use depending on where you're located in the world. All of these safe distance calculations are predicated upon a 90-degree entry into the field. So if we see here, we have a host guest set up. If we enter the field from this direction, we also need to take into account that you can also enter the field from the bottom light curtain as well. So if our safety distance is calculated from this light curtain, it may not be the same calculated from the guest portion of the light curtain. So that also has to be calculated in a separate calculation, and we may have to move this further down or further out. So what if we're using our AOPD in a horizontal configuration? Well, we have our minimum height that we also need to look at, our resolution. So in this situation, we need to look at, depending on the height of the light curtain, will determine our safe distance based upon the fact that a person could step into this field and, a full human step before actually triggering any part of this light curtain. Another AOPD that has a little different calculation is a rotoscan or an area scanner. These have to be assumed that they are mounted at a particular height. Normally it's 12 inches. And even at 12 inches, our depth of penetration is going to be 48 inches. That is basically how far a person can take a step into that field before being detected. Another thing to look at is safety mats, which are not as popular, but we do see those from time to time. For a safety mat, the safety distance must take into account the operator's pace and stride, assuming the operator is walking and the safety mats are mounted onto the floor, which in general they are. The operator's first step onto the mat is the depth of penetration factor of 1,200 millimeters or 48 inches. So in a safety mat mounted on the floor, depth of penetration is always going to be 48 inches. So simple thing to remember, easy to do. One thing we need to take into account of, though, is if that safety mat is not mounted on the floor. Let's say it's on a platform that is a step up or 2 steps up. If the operator must step up onto the platform, then the depth of penetration factor can be reduced by a factor of 40% of the height of the step. So if you have a 10-inch step, we can reduce our safety distance by 4 inches, and so on from there. So let's say maybe you don't like doing all these calculations. There's always the stop time measurement device you can use. So what is a stop time measurement device? It's a device that consists of 3 major components. The meter, which is the box here, which contains the processor with the electronics and the display. You have a position velocity transducer, which is basically a string pot encoder. And then we have the handheld actuator, which automatically releases or pushes a button if you're doing it for a 2-hand control device or an e-stop. Or it can also be used to operate a flag when you're using a presence sensing device, such as a light curtain or a rotoscan. And it will stick the flag into the sensing field, triggering a machine stop. The string pot encoder will be placed on whatever the movement of the machine is you're going to test, whether it's a turning spindle or a hydraulic cylinder, anything like that. And it will sense when it stops moving based on the time that it puts the flag into the dangerous area. And then we'll take that, and you can actually set on the display to output either a time, or it will actually do the calculation for you and tell you exactly the safe distance based on the time that it found. The nice thing about these stop time measurement devices is that you don't have to add the response time of the controller, the response time of the light curtain, and the response time of the machine, because they're all in line with each other. And by us using the stop time measurement device, it's already being calculated. We also have a couple other tools available to us. If you go to our German website, www.leuze.de, or to safetyatwork.leuze.de, we have some web-based tools we can use to help calculate these safety distances. You can see we have fields we can put into here, our distance to the safety zone, stopping time of the machine, depth of penetration, and then we can just hit a calculate button and it will do it all for us. We can also look at different scenarios approaching at a right angle, 14 to 40 millimeter resolution, with additional control functions, parallel approach, specific angles, multiple light beam devices, and laser scanners. So a lot of good tools that are available to us to make this a much easier process. So that's it for today. Next week's topic will be the requirements for muting, blanking, and initiation, some of the extended functions that we offer on light curtains and you'll see out in the field. So we will see you next week at 2 o'clock. Again, if there are any questions, you can always talk to myself or Mark Smokowitz, our Safety Product Manager. Any application questions or any topics you'd like to see in the future, be sure and let us know. Okay. Well, we will see you next week.